All right, so today we are going to be moving on to section 10.6 in our books, which is the introduction to parametric equations. So we're going to start off by learning how to parameterize a line. So why do we need parametric equations? So let's look at the following example. Two airplanes are flying at the same altitude and are following linear paths. Will the two planes crash into each other? So go ahead and graph these two lines, plane one, plane two, and let's see if they intersect. So we graph the two lines. The blue line is the first plane and the green line is the second plane. And it does appear that they intersect at 3,5. But what are we not considering, right? We're not considering time. Yes, they are at the same place, 3,5, but are they at the same place at the exact time? And that's what a parametric equation does, is it takes into account a third parameter, and in this case it would be time. So not just position, but position with respect to time. So equations involving two variables that can be graphed on a coordinate plane, just like y equals 2x minus 1 and y equals negative 1/3 x plus 6, are what we call as rectangular equations. And we can write rectangular equations as a set of parametric equations with each variable in terms of a third variable called the parameter. So the parameter is often time, but it can be other concepts such as angle or speed. And the parameter determines the direction and the orientation or speed of the graph. So let's look at the same two planes from above, but this time let's add a third parameter, time. So airplane one, this is a set of parametric equations that represents airplane one. And airplane two, here's the set of parametric equations that represents airplane two. So how are we going to graph these parametric equations? Well, we're going to make a table of values. So let's find our x coordinates with respect to time and our y coordinates with respect to time. So we go ahead and we substitute in 0 for t, and we get our coordinates. Substitute 1 in for t, we get our coordinates. 2 in for t, we get our coordinates. And well, bam, we end up with the following table. So graphing this, we have 1, 1, and that's when time is 0. And then we have 2, 3. That's when time is 1. And then we have 3, 5. And that's when time is 2. So maybe it's 2 seconds, 2 minutes, 2 hours. Without it telling us, we don't really know. We just know it's at that time. And then 4, 7 at time equals 3, and then 5, 9 at time equals 4. So the direction is moving that direction. So we have 3 things that we need to graph when we're graphing a parametric equation. Arrows to show the direction, time to show position at time, and then of course the actual position. So these 3 components together make up the graphic parametric equations. So now let's look at airplane number 2. So doing the same thing that we did before, taking our t, substituting it into our 2 equations to get out x and y at that time, we get our table of values. And now let's graph that table of values. So at time equals 0, our plane's at -6.8. At time equals 1, we're at -3.7. So that's at 0 and at 1. And at time equals 2, we're at 0.6. And at time equals 3, we're at 3.5. And at time equals 4, we're at 6.4. So again, couple direction arrows to show the direction, and then our time to show the position over time. So yes, the two planes are at that same position, but are they at that same position at the same time? No, they get there at different times. Plane 1 arrives at that position at 2, time equals 2, and plane 3 gets there at time equals 3. So maybe it's a minute later, maybe it's 3 hours later, whatever or an hour later, whatever the measure of time is. But if they are not there at the same time, so actually no, these two planes will not intersect, despite what the initial graph looked like. So that's what a parametric equation does. Is a parametric equation will give you, in this case, if our parameter is time, will give you location over time. So you can graph parametric equations in your calculator. We're not really going to do that today, but I wanted to make sure we got the directions to do so today. Go to mode and then change. Right now, you should have function. We're going to change that to parametric. And simultaneous means that it's going to graph both equations at the exact same time. And then type in, well, now when you go to your y equals, it should look like a parametric equation. It'll have a set of x1, y1, and a set of x2, y2 for your two sets of parametric equations. And when you use your variable button now, it will automatically put a t in for you. So it's a parametric equation. Change your window if necessary, and then look at the graph, compare the tables, and use the trace feature to see if the planes crash. So actually, you know what? Let's practice that. Let's get out our calculators. So I thought that I had a digital TI-84 on here. I do not. So I'm going to just show you right on my screen. So give me a second. And there we go. There's my face, very large. Okay, so we're going to start by hitting mode. So we hit mode, and then we should get a bunch of options. We're going to scroll down to for me, it's the fourth option. It says function. We're going to scroll over to select parametric. So it's the second option, and hit enter. So now I have parametric selected, and then we're going to scroll down to sequential, and again select simultaneous instead of sequential. So we changed function to parametric and sequential to simultaneous. So now when we hit our y equals, there you go, we get a set of parametric equations. So looking at that, re-entering in our equations, we have 1 plus t, so we do 1 plus, we hit our variable button, and when we hit our variable button, notice it says t. And now we're going to enter in our next one, 1 plus 2t, and notice again it says t, so there's our first plane. And then we're going to go to our second one, so -6 plus 3t, and then 8 minus t. And again, we got the t in there just by hitting our normal variable button, the x theta, etc., and it automatically put t in there. So I do not need to mess around with the window at all when I graph it. In the normal 10 by 10 works, because again, we know the table, we know what the graph looks like, so we don't need to worry about changing our window. So our normal 10 by 10 should work. So we type it in and there it is. So one thing that we can do is if you go into your window, mine graphed really fast. If we want to make it graph a little bit slower, we can change what our t step is. And for example, we could have our t step going by mine's going by 0.13. I could make it smaller, like 0.05. And then when I hit graph, notice it goes a lot slower, and we can see that the planes are there at different times. All right, so that's graphing a parametric equation in your calculator. Go back to our SMART lesson. All right, so that's two ways that we just answered this question. One was by hand, making a table of values, graphing it, looking at it. Second one was in our calculator, graphing it and looking at it. Now, algebraically, you can determine if the two planes are going to intersect at the same time as well. And what you should do is you set your x's equal to each other, your y's equal to each other, and you determine if x and y meet at the same time. So we start by setting our x1 equal to our x2. So 1 plus t equals negative 6 plus 3t. Solve for t, and we get t equals 7/2. Do the same thing for y. So we get y1 equals y2. So we have 1 plus 2t equals 8 minus t. So 3t equals 7 and t equals 7/3. So that means that x and y are not at the same place at the same time. They're at the same place at different times. So since the times are different for when the x and y's are equal, the planes will not crash. So those are the 3 different ways that we can go about doing this problem: graphing it by hand, graphing it in a calculator, or algebraically solving for the intersection. All right, writing a set of parametric equations from a graph or rectangular equation of a line. There are infinitely many correct answers if our line has no context. So how do you do this? Well, you need 2 things, the same 2 things you need for rectangular. You need a point and you need a slope. So once you have your point, x1, y1, and you have your slope, x2, or your slope, change in y over change in x, or b over a, we can put them together to create a set of parametric equations. So all a parametric equation does is it takes a rectangular, which mixes x and y together, and it separates it. And it says, what's just happening to our x values over time? What's just happening to our y values over time? So if we're looking at just our x values, we have x is starting here, x is starting there. So maybe I should change that to yellow. X is starting there, and then A will refer to our change over time, meaning our x component of our slope, or our change in x, or our run. And then if we're looking at the y component, same thing, it says y, where does y start and how does y change? So what's our y coordinate of our point and what's our y component of our slope? So let's look at this equation, y equals negative 4x minus 1, and let's create a parametric equation for it. So one possibility would be using a point we know that's on the line, our y-intercept, 0, negative 1. And then our other way is using our slope, which is negative 4 over 1. So again, we have what's happening to x. X is starting at 0, and slope, remember, change in y over change in x. So slope is increasing 1 every second. So 0 plus 1t. And then what's happening to y? Y is starting at -1 and is decreasing 4 every second. So -1 minus 4t. And there's our parametric equations. We could simplify and make it just t because we don't need the 0 there. All right, our second example, clean that up because it'll be in the way. We can keep the same point, but instead of saying that we're increasing x by 1 and decreasing y by 4 every second, we can change the direction and say that we're increasing y by 4 but decreasing x by 1 every second. So if we're thinking about slope, instead of going down 4, right 1, I could go up 4, left 1. So how do I take that? Well, again, look at the x. I'm starting at 0, but now I'm decreasing 1 every second. So 0 minus 1t. And look at our y. My y coordinate starts at -1, but increases 4 every second. So -1 plus 4t. And there are infinitely many correct answers. So for example, I could change any one of these slopes. So instead of 4 over -1, I could make this be 8 over -2. And now this is -2t, and that's 8t. Or I could pick a different point on my line, and instead I could use the point 2 comma, let's see, that's 2 is -8 minus 1, -9, 2 comma -9. So now this is 2, and that's -9. As long as x, y represents a point on the line and change in y over change in x gives us our slope, it's a correct equation of that line. So let's look at an example here. Our third example, I fixed your x parametric equation already. You just need to come up with the y component of the parametric equation. So what this means is my x coordinate is 1. I cannot pick any y coordinate now. I have to pick the y coordinate that corresponds with that x coordinate. So let's see, when x is 1, we have y is -4 times 1 minus 1, which is -5. And again, I can't have any change in t. For y, I have to have the change in t that gives me a slope of -4. So slope is, again, change in y over change in x. So if my change in x is 2, my change in y has to be -8. So that we end up getting a slope of -4. So there's my set of parametric equations for that line. 3 different sets of parametric equations for that line. And just to reiterate, all 3 sets above will have the same line as a graph with different starting points, speed, and direction. So same line, just different chunks of it and different speeds. Writing a rectangular equation of a line from a set of parametric equation, our goal is to eliminate our parameter t. So method 1, solve for t and substitute it into the other equation. So I could take x minus 6t and solve it for t. Subtract the 6 over, divide by -9, substitute it in to our y equation. So we get y equals 4 plus 6t, which means y equals 4 plus 6 times x minus 6 over -9. Distribute in the 6, and we get y equals 4 minus 6 times x plus 36/9. Combine our like terms, and we get, simplify that fraction, and then combine like terms, and we end up getting our answer. That is the method that you will use most of the time because it works for any type of rectangular. You can go from linear, you can go do a parabola, you can do any sort of conic with this method of eliminating t. Now the second method only works because it's a line, and if you know a point and you know your slope, then you can come up with an equation of a line. So I call this the Math 1 method because it's the exact same thing that we would have done when we were in Math 1. So in order to do this, we can take the fact that 6, 4 is a coordinate on our line, and our slope is change in y over change in x. So 6 over -9, and substitute it into point slope form, solve for y. Or you could substitute it into y equals mx plus b with y equals mx plus b and solve for b that way. But either way, you end up with our equation. All right, our last example. You are at the point -7, -3 at noon, and you were at 5:0 at 6 p.m. Let t equal time in hours where t equals 0 is noon, t equals 1 is 1 p.m., etc. Okay, graph the path from noon to 8 p.m. and label your graph. So at -7, -3, we're at noon, so noon's time equals 0. So that's this initial point here. And then we know that at 5:0 is 6 p.m. So that's when time equals 6. So we need to figure out, because we need to graph until time equals 8. So let's see what our total change is over that 6-hour period. So our total change in y over that 6-hour period was 3. And our total change in x over that 6-hour period is 12. So that means that every hour we have 1/2 up 1/2 over 2, up 1/2 over 2. So if we continue that pattern at time equals 7, we're at 7 1/2, and then at time equals 8, we're at 9 1. And then putting our points in between to show where we were at 1 hour, 2 hours, 3 hours, 4 hours. Easiest to start with the 2 and the 4 because those are nice integer values, and then our in-betweens. So B, write a set of parametric equations for your path in terms of t. And now there's only one correct answer because our answer actually has context. So when I substitute in 0, I need to get this point -7, -3. When I substitute in 8, I need to get that point 9 1. So we actually need to represent this very specific speed and direction. So our initial point is our initial point wherever time equals 0. So in that case, it's -7, -3. And then our change in y over time is up 1/2, right? And then our change in x every hour is to the right 3. So we put that together and we get x equals -7 plus 2t. Sorry, I think I said right 3, I meant right 2, because 12 hours over 4 hours means we're going to the right 2. Up 1, right 2, up 1, right 2. Sorry about that. Okay. And then our change in in y, we're starting at -3, and then we're increasing by 1/2 every hour. So we have up 1/2 every hour. So there's our parametric equations. So now part C says use these parametric equations to determine your location at midnight. So then we substitute in 12 and we end up getting our answer 17.3. All right, so I hope this lesson was informative and hopefully you are able to complete tonight's homework fairly easily. Again, keep track of any questions you have over these notes, any questions you have over the homework, and I hope to see you all during office hours. Stay safe, stay healthy, and please, please, please stay distant. Bye.